Hey guys, Dr. J. We're back with our discussion of Chapter 1 review. Okay, so let me get the whiteboard open, and now we're going to head on to a new concept. So, question is how to calculate average speed. So, how do we calculate average speed? Okay, so average speed is equal to distance traveled, that's the total distance traveled, divided by time. So the total amount of time that it took somebody to go that distance. So for instance, if someone traveled 240 miles in 6 hours, what would the person's average speed be? Well, you'd have 240 miles divided by, let's connect there, divided by 6 hours. That would give us 40 miles per hour. Okay, so that's a quick average speed calculation. And I want you to try this out on page 38, problem number 5. Go for it. Okay, so let's get this all cleared off. And now we're going to talk about centripetal acceleration. Okay, so we're talking about centripetal acceleration. So what in the world is centripetal acceleration? So let's say that I'm holding, okay, a string, and tied to that string is a tennis ball, okay? And I'm twirling that tennis ball in a circle. And so it's just going around and around and around. Well, acceleration means increased velocity in some particular direction, right? And it turns out that anything that's going around in a circle like that, even if it's going at constant speed, okay, that thing is actually accelerating. So there's an acceleration vector associated with it at any point in time. It's always accelerating toward the center. So if you've got something that's turning at constant velocity, even if it's just sort of rounding a corner, while whatever you have is, it starts here and then it rounds the corner over here, while it's rounding the corner, it's actually accelerating toward the center, okay, toward the center of that turn. So something that's turning around a circle or going around in a circle is actually accelerating toward the inside. That's why when you make a hard turn in a car, you might feel like the door is pushing you toward the middle of the car. Okay, if you're up against the door and you're turning away from the side of the door. Okay, so you might feel like you're getting pushed in. All right. So that's how centripetal acceleration works. Just like very briefly. I want you to try page 38, number 6, okay? And come on back when you're done.
Tell them that acceleration means speeding up or slowing down.
All right, so now we're going to talk about interpreting distance versus time graphs, okay? And I've relocated slightly so we can do this out of earshot of a conversation that's happening while the other, like a few of the other teachers have lunch. So here we are. So we got a nice little background here. We got some trees here. It's pretty nice over on this side of the building. Okay, so interpreting distance versus time graphs. All right, so let's say that you live a kilometer from school, okay? So you live 1,000 meters, right? Or let's say 4 people live 1,000 meters from school. Okay, so they all got to go to school. They live in the same neighborhood, very close to each other, but they're all about a kilometer from school. Okay, you got 4 different guys. Okay, 4 different guys. And your first guy is Jake. Okay, and Jake, right? Jake's graph is represented by the blue curve. Okay, represented by the blue curve. And let's say that we're going to measure time in minutes. Okay, and that's 20 minutes. Okay. So these guys are basically going to get to, they're all going to get to school in 20 minutes. Okay, so they're all going to wind up right there. but they're going to go about their travels differently. Okay. So Jake fancies himself a sprinter, right? So he starts from the beginning going really fast, and he goes very fast at first, but he runs out of gas and he has to slow down for a while. Okay. He has to stop. So he starts by immediately, right, within the first 5 minutes or so, going most of the distance. He goes 700 meters in 5 minutes. Dude's pretty quick, okay? But then he has to stop. He has to stop over here because he's just like super exhausted, right? And he says, uh-oh, that was just too much. It took too much out of me. And then the rest of the way, he just kind of walks in at a steady pace, okay? At a steady pace. That's how he gets there. And then we got our buddy Mario. Okay, Mario over here. Mario is kind of the opposite of Jake, right? He doesn't really want to get there. He wants to like sort of like lollygag around and go with his friends. And, you know, he kind of starts out just kind of goofing around back at home. And then he gets, you know, to talking to some people and they're just not going very fast. But then he remembers that his mom is going to get on his case if he doesn't get to school in time. So he books it. He books it on in and goes fast to get to school. Okay. So that's how he rolls. So he starts off going pretty slowly, then he accelerates steadily, okay, toward the end of his trip to get to school. Okay, so over here, what we have from Jake, right, in this area, this is deceleration. What we have from Mario in this area is acceleration. So deceleration. And then we have acceleration. Okay, and we can tell that we have deceleration because the slope is decreasing. The slope of the line is going down. The slope of the curve is going down. Okay, and we can tell we have acceleration because the slope of the curve is going up. Okay, so what about our buddy Becky? Becky, okay, Becky's like Miss Consistency, okay? She takes off at the same time and she gets to school at the same time every day, always walking at the same pace. So she walks at constant velocity, okay? So what Becky gives us is constant speed or constant velocity, okay? Because her slope doesn't change. So constant velocity, and we'll go with constant velocity, okay? Which means slope doesn't change. Okay, and now, what about poor Fred? Okay, so Fred actually lives a little bit closer to school than the rest of the guys. Okay, Fred lives right here. He lives halfway. He lives at the 500-meter mark. But Fred walks out of his house, okay? And he gets hit by a car, all right? And unfortunately, Fred is dead. All right, Fred's dead. And what that means is he's not going anywhere, okay? His velocity is 0. So if slope equals 0, what you have is someone who is stopped, okay? So no velocity, okay? Someone who's just stopped, all right? And so that's how we interpret one of these distance versus time graphs. Okay, and so now I want you to try page 38, number 7. Okay, page 38, number 7. Go for it, and then come on back when you're done. Okay, So now we're going to talk about units of acceleration. So that's what's up next, units of acceleration. Okay, and so one more thing before we get to units of acceleration. One thing that you can also do after the discussion we've just had is page 38, number 12, okay? Now that we've discussed distance versus time graphs that have some stopping going on, you should be able to extend that understanding to number 12. So go ahead and give that a shot, and then we'll come on back and we'll talk about units of acceleration. Okay, so when we talk here about units of acceleration, we'll do so within the context of a graph. And we'll consider a sprinter, all right? So we have a sprinter who gets to, over the first 5 seconds of a sprint, okay? The sprinter starts at time equals 0 and velocity equals 0 meters per second and proceeds from sort of like a steady jog up to a sprint over the first 5 seconds to begin going 10 meters per second. That's pretty fast. That's a pretty good sprint, okay? So we might ask ourselves, well, what is this person's acceleration, right? How fast is that acceleration? So acceleration equals change in velocity over some amount of time. So in this case, this person goes from 0 to 10 meters per second, okay? So 10 meters per second minus 0 meters per second, so 10 minus 0, and the unit is meters per second, all over 5 seconds. 5 seconds. So what you're gonna have is 10 over 5, right? Meters per second over seconds, okay? That's gonna equal, and my 5 looks like an S, so let me just go ahead and rewrite the 5. Okay, that's gonna give you 2 meters per second all over seconds, which actually equals 2 meters per second squared. So any acceleration value that you have is going to give you any acceleration unit will be composed of a distance unit on top and then 2 time units in the denominator, okay? So a distance unit in the numerator and 2 time units in the denominator. Okay, so please try page 38, number 8, okay? That's what you're up to. Good luck, and then come on back. All right, so I'm gonna clear this guy off. Okay, so now we're going to discuss representing velocity with vectors. Okay, so what in the world is a vector? It's actually pretty simple, but let's get this definition down, and then we'll go through some examples to help illustrate what vectors are, okay? So a vector looks like an arrow, and the vector's orientation represents its direction, while the vector's length represents its magnitude. Okay, so what are we talking about, right? What's an example? So I like to play golf, right? And when I hit my driver, which is the biggest club in the bag, okay, it's the one that hits the ball the farthest, I might start from the tee box and I might hit toward the hole, right? And if I hit the driver well, I'll give the driver about 135. So I'll hit my ball at toward the hole at about 135 miles per hour, okay? So that vector represents the fact that I'm hitting my golf ball, right? And I'll draw a little golf hole over here. So here's a little flag, right? There's a little hole, okay? There's the green, so I'm going toward the hole. I'll hit the ball toward the hole at 135 miles per hour, okay? So this is my golf ball. Okay, that's my golf ball. Now a tour pro, okay, a tour professional will also hit it toward the hole. I'm pretty accurate. I don't tend to hit it too offline, so I hit it toward the hole, but a tour pro is stronger than I am and hits the ball harder than I do. So that tour pro is going to hit the golf ball at about 175 miles per hour, okay? So that Tour Pro is going to hit it significantly harder than I will, okay? I'm not bad, but that Tour Pro is a cut above, right? That is why that person's playing golf for a living on the most competitive tour in the world, okay? So a Tour Pro hits it at 175 miles per hour, also toward the hole. So in this case, these two vectors, these two arrows that represent the velocities of our golf balls are going in the same direction, but they have different magnitudes, okay? So these two guys over here, all right, these vectors have same direction, but they have different magnitude. Okay, different magnitudes. So what's another quick example to help us understand vectors, right? Well, let's say we've got two cars going down a street. Okay, so here's a street. And one car is going this way at 40 miles per hour. And another car is going this way at 40 miles per hour. So these two vectors have the same magnitude, but they have different directions. Okay, different directions. All right, and there's a lot to discuss regarding vectors. Okay, it's a long unit. You're going to learn about it in math. You'll see it again in high school physics. We'll probably use vectors again over the course of this year. But for right now, I want you to check out page 38, number 9. Okay, you got this. I forgot about this problem. With this particular problem, so this guy's going east, this other person's going east, but they're at different speeds, so that's out. This person's going west, this other person's going west. They're going the same. Okay, so you can actually reason your way through this. Okay, so sorry, this is a good problem. Go ahead and do this problem, and then we'll come on back to the whiteboard. So here we are, back at the whiteboard. Okay, and there's one more problem type that I want to give you help with. Okay, so this is going to be the last one that we work on together, and it's this long, like, convoluted multi-step average speed calculation. Okay, so we're going to talk about this multi-step average speed calculation. So let's go ahead and come up with a real example here, like a real world example. So let's go through my average trip to Prescott, Arizona. Okay. So we're going to break this thing down and then we're going to talk about it. So we live here in San Diego, right? This is where I live, and you do too. And my parents, or at least in this general area, I know some of us might live south of the border. And then my parents live in Prescott Valley, Arizona. Okay, so Prescott Valley, Arizona is 435 miles away from San Diego, and it takes about 6.5 hours to get there, right? So we can do a quick little calculation to begin with to see what our average speed should be, right? So you've got 435 miles divided by 6.5 hours, right? So what should we get for our average speed? Well, if you do that division, you're going to get roughly 67 miles per hour. Okay, so I'm going about 70 miles per hour on average through that trip if I get there that fast. Realistically, I actually don't get there that quickly. It takes me a little bit longer. So let's go ahead and talk about what that trip looks like, okay? So I'm gonna zoom in here. And let me undo my annotation. So let me go ahead and zoom in on this guy. All right, so realistically, how do I do this trip, right? So I'm actually gonna travel from San Diego, and I'm probably not gonna stop until I get to Yuma. Okay, Yuma's over here. And so if you look at that distance, right? San Diego's here, Yuma's here. Where's my distance legend on this map? Does it give me a distance legend? I'm not seeing one. So San Diego to Yuma, let's go to Yuma first. So from San Diego to Yuma. In fact, I'll go ahead and just boil all this down to bullet points so we don't have to stare at this map for a while like this. And then we'll head back to the main session, okay? So we'll head back to the whiteboard. So this is what I'm doing. I'm gonna break this down. I go to Yuma, and then I usually stop somewhere in here at Gila Bend. So give me a tick to annotate this for us. So I usually stop right here around Gila Bend. And then I roll all the way through Phoenix to Prescott Valley. So I take this trip in like 1, 2, 3 legs. Okay, San Diego to Yuma, Yuma to Gila Bend, and then Gila Bend to Prescott Valley. So I'm gonna get all that stuff written out in a way that makes sense. We're gonna learn how to do these multi-step calculations. Okay, let's go ahead and pause this bad boy. Okay, so I went through the map, and here's my average drive to see my parents. So I leave San Diego, and I get to Yuma, Arizona, which is about 180 miles away in about 2.5 hours. Okay, so I'm going 180 miles in 2.5 hours. I then go at 65 miles per hour for 2 hours to reach Gila Bend, Arizona. Okay, and then finally, I travel the final 150 miles in 2.5 hours to get to my parents' place in Prescott Valley, Arizona. Okay, so remember, average speed, this all seems like a lot of craziness going on here, but we can break this thing down pretty quickly. If we just understand that average speed, right, is total distance, okay? Total distance over total time. All right, so what's going on? What's our total distance, right? So our total distance is gonna be the sum of all the little distances. So 180 miles to start with, okay? Plus 65 miles per hour for 2 hours. Well, 2 times 65 miles per hour is gonna give me 130 miles. Okay, and then finally 150 miles. Okay, and then what's my total time? 2.5 hours plus 2 hours, right? So the 2 hours here, plus the final 2.5 hours. Okay, so this is all gonna turn into roughly 460 divided by, and this is an approximation here, divided by 7, which is going to come out to, what is that bad boy? So 6, it's 420, so 6, and you 40 over 7. Yeah, it's about 6.5 hours. So that's roughly 6.5 hours. That's gonna be like 5, let's go with 6.5, let's go with 6.57 hours, sorry, 6.5, so sorry. That's gonna be roughly 66 miles per hour. Okay, roughly 66 miles per hour. I could do the calculation out perfectly, but there's no need, okay? So that's gonna be roughly 66 miles per hour, that trip. So that's a pretty good agreement with the 67 that we got earlier, okay? That's a nice little agreement with what we saw earlier just by doing an approximation, okay? So this type of calculation you can apply to page 39, number 13, okay? Page 39, number 13. And that's the last problem in your problem set that I'm gonna provide this much help for, okay? So you've learned a lot. Go ahead and apply what you've learned. Don't try to remember. Think, all right? And good luck with your chapter 1 review, all right? And as always, may all the forces be with you.